A trebuchet is a siege weapon typically associated with the medieval era. Counterweight trebuchets convert the potential energy of a heavy counterweight to kinetic energy in the projectile. Large trebuchets are capable of throwing 90-kilogram masses a range of 300 meters. Ours, however, is quite a lot smaller. Historically, trebuchets were aimed using range tables and distance estimates. The counterweights would be raised using human effort, and achieving any rotational variation in the firing arc was unheard of. Our project aims to tackle these problems through the wonders of computers, computer vision, and electrical actuators. Our trebuchet uses a camera to detect QR codes. These QR codes allow the onboard microprocessor to determine required rotation and the range of the target, which commands a winch to raise the counterweight to the correct height to hit the target. This allows our trebuchet to be more versatile and repeatably accurate than its medieval counterparts.
To optimize our trebuchet, we first had to simulate it. The constraining interactions between the projectile and the arm, and the projectile on the ground, made it extremely difficult and largely infeasible to simulate it using conventional Newtonian mechanics. Enter Lagrangian mechanics, a method of deriving equations of motion specifically designed for systems with constraints. In principle, Lagrangian mechanics is duck soup. Define the Lagrangian, the difference between kinetic and potential energy, based on an arbitrary number of state variables and the derivatives. The partial derivative of the Lagrangian, with respect to each state variable, is then equal to the time derivative of the Lagrangian with respect to the time derivative of that state variable. With a bit of calculus, one can then simply solve for the second derivative of each of the state variables. With those obtained, we used MATLAB to solve the resulting second-order differential equations. We ran many simulations that compared trebuchet dimensions like mass ratios, arm length ratios, and the ratio of arm length to fulcrum height, and their effect on maximum projectile range. We then chose the combinations of dimensions that should optimize for the maximum range, and implemented them in our actual design.
Our trebuchet is constructed of laser-cut MDF and stands roughly 16 inches tall. With its 4-pound counterweight, it can throw a 2-ounce projectile across the room and has proven successful at damaging walls. The A-frame that supports its 17-inch arm rests on a Lazy Susan, directly driven by a servo. A winch pulls down the throwing arm, lifting the counterweight to the proper position prior to firing. To ensure rigidity and strength in our bonds, copious amounts of duct tape and hot glue were used.
The trebuchet first determines the location of its target using computer vision. Because our camera is precisely calibrated and the target is an AR tag with known dimensions, we can use the size and location of the target in the camera frame to determine its position relative to the trebuchet. The trebuchet then rotates its Lazy Susan to place the target directly in front of the arm, and does a quick double check with another round of AR tag recognition once it reaches the desired position, just to make sure that the servo executed the turn correctly. Then it consults a table, computed from the trebuchet mechanics, to determine what initial angle is necessary to hit the target given its distance and height from the trebuchet. A servo rotates a pulley to raise the counterweight to this ascribed height. The arm is then released from the servo, flinging the lead projectile perfectly towards the target.
Fire in the hole.